Hello, welcome to my second presentation on software-hardware interface design. I'm Okbayasu. I'm going to present control design for hardware interface in my second presentation. So let's start with the learning goals. After watching to this presentation, you should know the activity for control design in a coprocessor, and you should be able to distinguish or differentiate between a command and a configuration, and know the techniques used to optimize the performance of a coprocessor. Let's start with the control design. Control design in coprocessor is the collection of activities to generate a control signal and to capture a status signal. The slides shows the generic architecture to control a custom hardware module through a software, which is shown on the right side of the slide. The command interpreter accepts command from a software and returns status information. It is a top-level controller in the coprocessor, and it communicates directly with software. The command is a one-time control operation, while a configuration is a value which will affect the execution of the processor over an extended period of time, possibly over multiple commands. Here the distinction is that's a one-time control operation, while that is the value that affects our system over extended period of time. We have several architectural techniques that can be used to optimize the performance of a coprocessor. Some of them are hierarchical control and control of internal pipelining. Let's start to see the hierarchical control. The hierarchical control architecture of a coprocessor that can achieve communication or computation overlap. In hierarchical control, we use a simple start-done handshake for uniterated components on the hierarchy. It has a hierarchy of controllers which allow independent control of the input buffering, the computation, and the output buffering. A control hierarchy simplifies the design of a control as shown in the diagram in this slide. The command interpreter can easily adapt to the individual schedules from the input final state machine, from compute final state machine, and from the output final state machine. The methods of using start-done pulse is insufficient when working with a pipelined submodules. If you have submodules that has a pipeline, then this way of working is insufficient, since a done pulse only appears after the pipeline latency of the submodules. Let's see the control pipelining. When a custom hardware module has internal pipeline stages, hierarchical control becomes more intricate. So we need to design our controls through the control of internal pipelining. And when we are designing, we have to address two issues. First is we need to find a way to generate a control signal for the pipeline stage, and then we need to define a proper mechanism to interface the control signal with the higher layer of controllers. A simple start done handshake is insufficient for a pipeline because it does not reflect the pipeline effect. Here it shows the control pipeline architecture, and it consists of a number of pipeline stages separated by pipeline registers. Here we have stage 1, stage 2, and stage 3. And the latency of the pipeline is the number of clock cycles it takes for an operand to move from the input, which is the data in, of the pipeline to the output, which is the data output. And the throughput of the pipeline measures the number of results produced per clock cycle. In any pipeline coprocessor, the control signal are eventually be under the control of the higher level controller. Here I make the dot 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 because in a linear pipelining this feedback is not there. In a nonlinear pipelining there is a feedback. That's why I show here with a dot line. We have two types of control of internal pipelining. One is the control of linear pipelining and the other is the control of nonlinear pipelining. In linear pipeline architecture, there are no feedback connections, so the latency equals the number of pipeline stages. If we have 3 stages, then the sum of the 3 latencies, and the throughput equals 1. In a nonlinear pipelining architecture, there are feedback connections, and the latency can be higher than the number of pipeline stages, and the throughput can be lower than 1. Here in nonlinear pipelining, the pipeline stages are reused multiple times per data item that enters the pipeline. As a result of the multiple entrants, the throughput of pipeline cannot longer be 1, so it is lower than 1. That means here it concludes my control design presentation. Thank you very much for listening to this presentation.